with first principles, right, or calculus in general, the one thing you want to understand, right, is why you'll be doing what you're doing and what it gives you. So this here, this formula, right, is called first principles, like the name, principles. This is a formula, it's on your formula sheet. And the one distinct item about this formula is the fact that this has this symbol, you see, f of x with this punctuation mark up there. It says lim, it's equal to lim h equals to 0, h f of x minus f of x of h. Now this formula, the idea is it will be taking you from an equation of y, right, f of x, going to an equation of f prime, if you will. So I'll just refer to the names of these two symbols, like the different ones, that will all just be meaning the same thing. Here, we know that they can call this f of x, or sometimes we can call it y, right? This, they call it f prime. However, you want to refer to this as gradient. See, because when you go from a standard equation, right, to an equation of f prime, this is called differentiation, or that's like let's be there. Differentiation. So going from f of x to f prime is differentiation. So you'll basically be going from an equation that gives you y values as an output if you give it x, to an equation that gives you gradient as an output if you give it x. So a visual illustration is, if you have a graph, say you have a parabola, say with a parabola, when you're starting off with a parabola, the different points on this parabola, right, 1, 2, 3, 4, going on and on. Remember, these different points are y values, you see. So we know that if you throw in x, right, your equation will give you y. You see, if you throw in x, it will give you y. Fine, that's how your equation of f of x works. But then once you have differentiated an equation, right, instead of your equation giving you x, it's going to be telling you the different gradients at those x values. So meaning if you're throwing in x, it's going to show you the specific gradient at that point. So this is not average gradient. Remember, average gradient, it's basically a matter of taking 2 points, one point somewhere here, another point somewhere there, and then using the gradient formula. This is not that. This is different. This is getting the exact gradient at the exact specific point. So meaning a point like here, right? You can get the gradient here. You can get the gradient, right, if you put in the x value. You see? So that's how the first derivative works. The only thing with the first derivative is that obviously, if you want, it will sometimes draw a graph, yes. However, apart from it also being able to draw a graph, the main idea is you always need to look at the outputs as different gradients at those specific x values. So as an example, if we have an equation that says y is equal to 3x squared, its first derivative, right? Or let me just put f of x, since we're dealing with f of x at the moment. Its first derivative would look like 6x. So the idea is, if you put the same x value here and the same x value here, it's the same x value, but it gives you two different things. You see, one gives you the y value. So if it's an x value of like 4, right, this is giving you 16 times 3, which is going to be 48. So this is a y value. You see? This here, if you put a 4 here, oh, sorry, I forgot to put f prime. I forgot to put that punctuation. Put a 4 here. 6 times 4 is 24. It's just a coincidence that one is half of the other. It's purely a coincidence. But all this is telling is this here is a y value, and then this here is gradient. Do you get it?
Yes, I see it.
Yeah. So, and it's important to make sure that you what is this? If you can remember this for all the calculus that you ever do, you'll be fine. So that's yeah. I don't know where my voice is going. But like I was shouting anything, or even talking a lot. Anyway, just to drink some water. But I think if you can hear me, it's fine. So that's more like, if you can think of the basics of calculus, this is what you should consider the basic. Knowing what f of x is and knowing what f prime is. So obviously, these differ. You know, the kind of equation that you start with, it will always differ. So if you check the playlist that I was referring to, right? This playlist here, the one, the calculus grade 12 playlist, it is, wait, oh, I'm already there. I'm already within the calculus grade 12 playlist. If you check, it starts off with, I think it was the limits there, showing what limits are. You know, that's not even something you really need to worry too much about at grade 12 level, because you hardly even go that deep. You know, the only time you'll probably use limits is when you're using the formula first principles. So first principles, this is just a formula that takes you from an original equation to a differentiated equation. It's a formula that takes you from having an equation that gives you y values, and it gives you an equation that gives you y values. It's like converting a formula. So that process is called differentiation. You can do it via formula. The other thing is you can also do it via a simple method that is not necessarily a formula, you see. So the simple method that you can also use, right, to differentiate an expression. So let's say here, you only use first principles if they tell you, you know, that's like one big issue. Only use first principles if they ask for it. And in any exam, they'll always ask for it once. If it's a class test or term test, maybe you might have 2 questions or more in first principles. But in a standard exam, final year exam, you'll never see more than one ever. You see? So what I can put here is only use when asked. You see? So with that being said, if you're just asked to differentiate, you know, let's say it's just a random question, then there are methods. There's a method rather in grade 12 that you can use. And so firstly, if you have an expression, let me use different, let me just put it this way. Let's put here differentiation. So with differentiation, the other thing is, you see, where you're starting off, remember we said that you can start with like y. You start off with an equation that gives you y, right? Y values. And we know that when you're referring to y, you can use f of x or you can use y. The idea is that with differentiation, it also has different ways you can refer to, you know, differentiation. So with the standard equation, right? Let's put here let's write here, if you start with f of x, right? When you differentiate the equation, you can write f prime. However, if they sometimes give you the equation, let's say they say y is equal to something instead of using f of x, when you differentiate it, you can write that the differentiated equation, you can write it using the symbol dy over dx. You see, the same way you use f of x for an original equation, you can use f prime if it has been differentiated. If they gave you the equation with y, the differentiated equation can be written as dy over dx. So the dy over dx just means difference in y divided by difference in x, which is almost pointing towards something like this equation. You see, it's not necessarily telling you that you're going to use this equation. It's just giving you the idea that you're getting gradient. And gradient is just the difference of y value over the difference of an x value. And it's not necessarily the distance, it's not necessarily the gradient formula. Because remember, we said this formula would be giving you the exact gradient at an exact point. So,
Can you give me an example with that, please?
yeah. So, as we said, for example, here, right, if your equation starts with y is equal to x squared, this can be the given equation. The differentiated equation, they'll just refer to it as dy over dx. It will just be 6x, for example. You see, so here is this is just a symbol. You see, it's just two different symbols that say the same thing. Remember, an equation can be given like with f of x, or it can be given with a y. That's all I'm trying to say. So I'm also then trying to say, since sometimes they can give you x, sometimes they can give you f of x, sometimes they can give you y. Since they can do that, for the differentiated equation, they can also sometimes either use f prime or dy over dx to refer to an equation that has been differentiated. It's just symbols.
Okay.
So with the symbols out of the way, now we need to work on how to go from this original equation, or I usually call it a graph. What do I normally call it? I normally call it the what you may call this here. You can call it you can call it the original equation, right? Because it's the one that like plots the graph, like the original graph. Well, different equations still plot graphs, but you need to know that those graphs will be telling you information about the original equation. You see, for example, this here can draw a straight line. However, the information on that straight line is telling you the gradients of this graph. That's what you want to always remember. But before going too deep into that, when you start with the equation, let's use f of x as an example. F of x, your equation, right, normally has a coefficient, a base, and an exponent. Now, this is where you learn the basic of calculus. To go from a standard equation to a differentiated equation, all you do is the following. You see, to go from this to f prime, all that happens is the exponent, you multiply it with the coefficient, and then you remove 1 from the exponent. An example is like what we are using here, the 3x squared. If you look at 3x squared, the coefficient is 3, the base is x, the exponent is a 2. Now, when you differentiate it, you just say 3 times the 2 up there, or rather, it's easier to say the exponent, you just multiply the coefficient. So you have 3 times 2, right? Then you remove 1 from the exponent. That's how you end up with 6x. You see it?
I see.
Yeah. So another example, we choose a basic one. You can have, let's say, 5x cubed as the starting equation. The differentiated version right, would be 15x squared, because you're saying 3 times 5, which is 15, 3 minus 1, which is a 2. Now, this is the same forever. Whenever you need to differentiate, it's always the exponent times the number in front, and then you remove the 1 from the exponent. So meaning even if the exponent is a negative, there you have f of x, or let's even use a different symbol. So you have g of x is equal to 4x to the power of minus 3. When this is differentiated, you can say g with the punctuation mark there. This is going to be negative 3 times 4, which is negative 12. Removing 1 from the exponent is going to give you negative 4. You see. So speaking of negatives, sometimes they can maybe even give you your equation with, let's say, 3 over x squared. You see, this is a different kind of a scenario. But before you can differentiate anything, right? Before you can differentiate anything, always make sure that you have written it in a standard form. So with your standard form, it means that you need to have a clear coefficient, a coefficient that you can clearly see, a specific base and a specific exponent. So from something like this, right, to get that, you would need to take the x squared up, meaning you would have 3x to the power of negative 2 squared. You see, this is not differentiated. It's still the same equation. You have just written it in a different format. You see, it's just like with normal math. Normally, depending on the kind of equation we get, we sometimes simplify it first, or we sometimes break it down first before we do what we want to do with it. That's the idea here with differentiation. That's one thing you actually always need to remember with differentiation. 99.99% of the time, we are going to have to rewrite the equation first into a format that has a coefficient, a base, and an exponent. The moment it at least has those 3 things one by one, you can now then differentiate, because anytime you will still just be working with the original equation, you keep the original symbol. You writing, you see here, k of x is equal to this. Because you have not yet differentiated, you're still just using k of x. The moment you differentiate, now you can use k prime. And then this is going to be 2 times the negative 2 times 3, which is negative 6. And then negative 2 minus 1 can give you negative 3. You see, so you just need to be careful there.
Okay. I have a question, right? You said that 9% of the time we have to change the equation. Is there a question where we can't change it into the standard form?
Yeah, that's the thing. You will always be able to. So if you see that you cannot change it, maybe it's because you don't know the way to change it. What I mean is, if they, for example, give you something like this, 5 square root of x, and they ask you to differentiate this, you obviously would need to change the third into a fraction and into an exponent, which is what we know is a half. Remember, anything under a square root symbol is to the power of a half. You remember that? Yeah. So you see, this is what you would need to do first, meaning this you would still be referring to it as h of x. So when you now differentiate, you can change the symbol now. A half times 5 is 5 over 2. Removing 1 from a half is just negative a half. You see it?
My I have another question. So you see, right? What was my question? Oh, I wanted to ask, right? Is it possible to find the f prime, the f prime, right, without using that same equation?
Without using this law,
Yes.
the only other way is to use first principles, which is the formula, but you only use it if they ask you. to use the formula. Remember, the formula is just long and unnecessary unless they ask for it. So the simple answer is no, there isn't. This is the only way to differentiate. Only thing is, you just need to be careful that you make sure that what you're differentiating is in this standard form. You see? So the idea is, you see, here you see it was not in standard form, but you made it in standard form first. Same with this question. You see? Now, normally, depending on the question, if they want you to have answers that have positive exponents, here, you can just take the x down and then the 3 will be a positive. Same here. You can just take the x down here where the 2 is, and then the exponent would be a plus. You see, that's if they specify that they want positive exponents. If they don't specify, you can just stop there. It's fine. Now, the other idea is, what we know is normally this is just like the basic one, right? You just have one single term. But in general, your expression will have multiple terms. You see, so maybe it can have, let's say here, let's now use maybe y. Here it can have y is equal to x squared minus 5x. If you had to differentiate this, right? Fortunately, this is in standard form. This is also in standard form. Because this one, the exponent, you can see it's just a 1 here. You see, the coefficient of x is also just a 1. So when this is differentiated, the differentiated equation would be referred to as dy over dx. So here, 2 times 1 is a 2. 2 minus 1 is a 1. Moving on to this one. 1 times negative 5 is negative 5. 1 minus 1 is minus 1. I mean, 1 minus 1 is 0. So instead of writing x to the power of 0, this one you leave it out. Because remember, anything to the power of 0 is a 1. Do you see?
No, I don't see. Maybe start again.
Yes. So we said that, remember, the law says you go from here, all you do is exponent multiplies the coefficient, and then you remove 1 from the exponent. So what I'm saying is, the original exponents here, you see the exponent here is a 2, and the exponent here is a 1. So on the exponents, when you remove 1 from here, you have 1, right? But then for the 1, you will eventually remove 1 here. So you'd end up with x to the power of 0. Because remember, 1 minus 1 is a 0. And x, anything to the power of 0 is a 1. So here you would just have 5 times 1 in front here, but you don't have to write it. So you just type a 5. You see?
I'm trying to figure out the dy, and I'm just really confused the dy part.
It's just a symbol. So here, this could have just been f of x. This would be f prime. Right? This is still just the same thing. It's not too different now.
Oh, I'm asking, how did you get the dy?
Yes. So the dy, we said we just used this. We said 2 times the 1. Remember, there's a 1 in front here, right? And remember, the exponent here, if it's not visible, it's also just a 1. So 2 times 1 gives you this 2. And 2 minus 1 gives you a 1. And here, 1 times minus 5 gives you minus 5. 1 minus 1 is a 0. You see? And then x to the power of 0 is just a 1.
Oh, so we treat them separately, basically.
Yes, you do one term at a time. So remember, we said each term just needs to be like this. You see, the first one has to have 1, 2, 3 things. Then the next one has to have the same thing. Meaning, if you say maybe you had something like y is equal to x let's see, 2 over x, right, minus 3 square root of x, and you had to differentiate this equation. Differentiating this equation, you start off by simplifying first. So you see the symbol is not changed. So simplifying, you need to at least have a coefficient, a base, and exponent for each of them. So starting with this, x, you can move it upwards. You're going to have 2 with x to the power of -1. This one, you can have 3 and x to the power of half. Do you agree?
Oh, yes, yes, I do.
Yes. So with that being said, let's see here. With that being said, right, now you would be able to differentiate, right? So differentiating this, -1 times 2 would be -2. And then -1 times -1 would be -2. And then here a half times -3 would be 3 over 2. And then a half minus 1 is minus a half.
Okay.
Mm.
Okay. I see. I have another question. So you see, right? How we did the entire thing, we were converting the same form to the different through differentiation, we take it to the prime, right? My question is, will there be a question whereby they asked us to do the opposite, turn the prime into the standard form?
Yeah, that's called integration. And in grade 12, you don't necessarily do integration. So the simple answer is no. If they do ask you to go back, it's normally a scenario where they would have to give you certain information that can allow you to go back. For example, if the only thing is, if the reason why they normally cannot ask you, or rather they don't, what you asked for, right, what you talked about right now, right, is going from f prime to f of x. This is called integration. You see, of which this is not within the scope of your syllabus. You see, not CAPS, not IEB. You don't do integration. Only after this year will you do integration. So the simple answer is no.
Why is integration not considered in the syllabus when it's just the opposite of what do you call this? How do you say this?
Differentiation.
Yeah. Why is it not included in just the opposite? Simply the opposite.
Yeah, because remember, there are multiple combinations that give you the same thing. So if the other thing is, right, if you have an equation like f of x is equal to 3x squared plus 5x plus 2. The idea is, what the law says, if you're going to be differentiating, right, this here, remember, this does not have a visible x. So if you think, so logically what you're seeing here is x to the power of 0, because here it's just x to the power of 2, x to the power of 1, and then if it keeps going, it's going to end up at x to the power of 0, right?
May you please repeat your question?
When you look at a standard equation, remember, all that happens is this is a quadratic equation. It starts with x squared, right? And then it moves to x to the power of 1, right? The next one just has x to the power of 0. We don't write it because x to the power of 0 is a 1. But what I'm trying to show is that an equation in standard form has decreasing exponent. This is 2, 1, 0.
Okay.
Yes. So what I'm trying to say is that when you're going to differentiate this, there's a law, right? Here we refer to this as a constant. You remember?
Yes.
Yes. So with differentiation, right, the derivative, when you differentiate a constant, it will always be a 0 all the time. That's the law. When you differentiate a constant, it will always be a 0. Reason is you always have 0 times the constant, and then you always just have a 0, because when you're differentiating this, you have 2 times 3, which is a 6, 2 minus 1, which is a 1. Then here 1 times 5, which is 5, and then 1 minus 1, which is a 0. And then this one now, 0 times 2 is a 0, and then anything times 0 will always be a 0. So the derivative of any constant is always a 0. So integration, you would be going back to the original equation. So you guessing what this constant is, you see, it's not something you can do. You cannot guess what the constant is. You would need to be given additional information, or rather, there are ways to be able to go back. Even this year, there are times where you will be required to go from from the differentiated one to the original one. But the thing is, the way it would be structured, they would have given you ample information for you to be able to say what this is, and what this is. And that's obviously like a bit far in the future. But then you are asking why there is no integration in grade 12, it's basically almost like asking why is there not any of the topics that fall onto all the work that you learn now. Because remember, it's just a level higher, and it's just work that has different applications. So if they do have integration in things like AP math, but in just pure math, they don't.
Oh, okay. Okay. But I'm gonna still learn it because I feel like when I have a question where it has to involve something the grade higher, I can't trust math anymore.
When
um
hold on. In a nutshell, there's no integration in this grade. So you don't have to learn integration. Obviously, as we're going to be doing what we'll be doing, we are going to at some point go through a question that may want us to get the original equation from the differentiated equation. And it's going to be the nature of the question that will allow us to see what to do. But it's not going to be something complicated. Because as you can see, if you have, say, this is a differentiated equation and this is uh, f prime, you see, there are not a lot of combinations that give you a 6. It's always just going to be 3 times 2 to get a 6. And
yeah.
for you to end up with a 5, it's obviously obvious that you started with x to the power 1. So some of these are obvious. So you then knowing what the constant was, they would sometimes then just give you a coordinate that the graph passes through, so that you can put in a y value, put in an x value here, put in an x value there, and then have a variable here that you can work out. You see?
Okay.
Yeah. So that's the idea behind what you said, so that you don't think it's let's say something that is going to be like a higher level question. It's actually not, because you see, to get a 6 is just 3 times 2. That's the only combination. But then the 6 and the 2, for you to know which one was the exponent and which one was the coefficient, you're just going to look at what you have here. You see, because if this ended up as a 1, obviously your exponent was not a 3. Because if it was a 3, you would have said 3 minus 1. So this would need to end up as a 2. So what I'm trying to say is, to go from this, if you're going to reverse it, you see, you need to know that, okay, there was something in front and there was x here. There was something at the top. And remember, we said to get a 6, it's just a combination of either 6 times 2, or you can even take it further and say it could have been 6 times 1. So in that situation, this can either be the 1 or this can be the 6, or vice versa. This can be a 2 or this can be 3, or vice versa. So if you start off with even trial and error, if you want to put a 1 here and a 6 here, this cannot be what it started off as, because if you had said 1 times 6, you would have had 6 in front, and then 1 minus 1, you'd have had a 0 here. So 6 and 1 is not what the original one was. Then you can test out the 3 and the 2. You can say, okay, maybe the exponent was a 3. So you could maybe put a 3 here and a 2 here. And you would say, okay, 3 times the 2 is what would have given us the 6. But then 3 minus 1 would have given us a 2. So that also doesn't work out, because the differentiated one has a 1 there. So in your testing, you would then say, okay, it looks as though it was actually the other way around. This one was the 3. Wait, 3 and 2, right? Yeah, this one was the 3, and this one is the 2. Because if you said 2 times 3, giving a 6 here, remove 1 from this, it's going to give you a 1. So that's how you would know, okay, fine. The original one had a 3 in front, it had a 2 as the exponent. You see, it's not a complicated scenario. It's just reversing how you could have gotten this 6. Do you see?
Okay.
Yeah. So that is that for what you just asked right now. So with all this being said, that this is more like the long and short of differentiation. If you wanna go from an original equation to a differentiated equation, you're gonna use this simple law here. Now the idea is, obviously this is where you need to know a few of the basics of simplifying. Like, for example, if you had an expression that maybe had y is equal to 3 square root of x to the power 5, and they want you to differentiate this equation, what you need to know is to rewrite this right in a way that you can differentiate. The 3 can be written under the 5 like that. Now when you then differentiate this, you can then say the 5 over 3 times the 1 in front here, give you 5 over 3, and then 5 over 3 minus the 1 minus 1 rather will give you 2 over 3, and this will be your final answer.
Okay.
Yeah.
Let me write my
So do you get this one?
yeah.
Yeah. So with all that has been said now, right? With this playlist as mentioned, right? The calculus grade 12 playlist. If you see what is there, you see it starts with the limits, and then it moves on to first principles. Once you have these two done, you don't have to ever go back to it, because the only, as we say, there's always going to be one question, and that's it. This tutorial here covers the basics of the formula we just used now, the one where you just take the exponent, multiply the coefficient, and you remove 1. And then here, this is just different examples where you have fractions and surds, just like what we also talked about in a situation like this one, where you have fractions that you have to deal with, and you also have some surds that you have to deal with. And then this is also then just going deeper into different expressions. You see, differentiating complicated expressions. And then it then moves on to working with now, for example, graphs. You see, equation of a tangent, again, equation of a tangent, how to differentiate using the power rule. So the power rule is what we have been talking about here. This is called the power rule. You see, this here is referred to as the power rule. You see, it's just another example. And then here again, more questions on with surds and fractions so that you have different ideas of how that works. And then here again, differentiating an expression that has pi. You see, remember pi is just a number. So there's also an example of that. And then here, equation of a tangent at a given line again also. So this playlist here goes hand in hand with the calculus grade 12 playlist. You see, of which that one is also, how did I end up here now? It goes hand in hand with the calculus grade 12 playlist, of which that playlist, you can see it's just under the calculus playlist there. If you go down here, you have the calculus grade 12 and then cubic functions grade 12. So going through these two playlists one by one, right? It's going to give you a bit of a huge advantage when it comes to this topic. So
Okay, thank you. May you please